So in this video, we're going to be looking at parallel circuits, but before we do, I'm just going to quickly recap series. So components are in series when they are one after another like this, and we know that the current flowing through this series circuit is constant throughout. So the current here is equal to the current here, all equal. However, the potential difference, so if we had 12 volts here, and if these are identical resistors or light globes, then it's going to be an equal voltage drop. So if it was 12 to begin with, it might be a 6 volt drop and then a 6 volt drop. And then if the resistances are different, there's going to be different voltage drops. But there is voltage drops across the series circuit. And these voltage drops add up to the voltage supplied. Now, resistance is simply added together. So if this is a 30 ohm resistor and a 50 ohm resistor, 30 plus 50 would be 80. So the resistance adds. However, now we're going to look at parallel circuits. So when components are parallel to one another, these two, if they're light globes, they're parallel to one another. And so if one globe blows and the electrons can't flow through, then it can still flow through. So our houses are often wired parallel. Now, the total current equals the sum of the individual currents, which we'll look at in a minute. So water streaming through here, some branches off here, some branches off here, but not water, it's electrons. So the electron flow is slowed. So some current goes this way, some current goes this way. But then when they join back here, this current and this current join back together, then this total current here and this total current here are equal. But we have this flow slowing down here and here. So the current reduces, but then adds back together. So the total current equals the sum of the individual currents. Now, what is handy is the potential difference in each loop. This is one loop, this is another loop. They're equal to one another, and they're equal to the voltage supplied by the battery or power source. So if there's 12 volt, this loop would get 12 volts, and this loop would get 12 volts. However, what is strange is that the resistance actually becomes smaller if you add more resistors. So when you add resistors in series, the total resistance is increased. However, what happens is when you add resistors in parallel, the total resistance actually slows down because there's more pathways for the electrons to flow. So the actual resistance in the circuit slows down by adding more resistors. And there'll be a formula to help you calculate this. So as I said, parallel circuit, the current split. So the total current coming in to this node is equal to all the individual streams. So this one plus this one plus this one would be equal to this. And they join back together, and then this current flowing through here will be equal to this one plus this one plus this one. However, the voltage across each one of these resistors is equal. So if this is 12 volt, this loop will get 12, this loop will get 12, this loop will get 12. So the currents split. However, the voltage is the same across each individual loop. Now, you don't need to memorize this or anything or even write it down, but I'm just going to show it to you. So this is technically called Kirchhoff's current law, where the current splits. Now, we know that voltage is equal to IR, so we can rearrange that. Voltage is IR, so we can rearrange that so that current is voltage divided by resistance. So we can replace this. So the total current is equal to the voltage divided by the total resistance, and current flowing through the first branch is equal to the voltage divided by that resistor, and the current flowing through the second branch is the voltage divided by the resistance in the second resistor. And because all the voltages are the same in parallel circuits, we can cancel them out, and we're left with 1 over the total resistance is equal to 1 over R1 plus 1 over R2. And we can use this to solve for the total resistance. And I'll show you how to do that in a minute. So in this example, we've got two resistors. They're in parallel with one another. We've got a 15 ohm resistor and a 10 ohm resistor, but they're connected in parallel. So the total resistance, or the total effective resistance, is what we want to calculate. So like I said before, it's not actually going to be 15 plus 10 because they're connected in parallel. It's actually going to reduce. So the way that we're going to do it is 1 over RT, which is our formula, is equal to 1 over R1 plus 1 over R2. And our two resistors are just 1 over the 15 ohm resistor plus 1 over the 10 ohm resistor. And if we type this into our calculator, 1 divided by 15, or 1/15 plus 1/10, is going to give us 1/6. So 1 over the total resistance is equal to 1 over 6. So you can very easily see that the total resistance is just going to be simply equal to 6 ohms. So by adding together a 15 and a 10 ohm resistor, we've actually reduced the resistance in the circuit to 6 ohms, which is crazy, but it's because there are now two branches for the electrons to flow through. So there's actually less overall total resistance. Now, if your calculator is not spitting out a nice fraction like this, and you get 1 over RT equals, I don't know, some decimal answer, this 0.05 isn't 1/6. I'm just showing you. If it spits out a decimal answer, what you need to do is you need to flip them. So to find RT, you technically would need to divide both sides by times both sides by RT, and then divide by the 0.05. So you get RT equals 1 over 0.05, which would be whatever your answer is. So if your calculator is spitting out in decimals, you need to do the rearranging yourself. But otherwise, if it's spitting out in fractions, you can just equate these two. So we're going to analyze the whole circuit. So we've got a 20 ohm resistor, a 60 ohm resistor. Let's just say that this is the 20, this is the 60. And they're connected in parallel, as shown in the diagram, with a 120 volt power source. Find the voltage and the current in each resistor. Well, the voltage flowing through the first resistor is going to be equal to the voltage supplied by the battery. That's 120 volts, and the voltage going through the second resistor is also just going to be 120. So voltage is always the same through the parallel loops. Now, the current. Well, we know that voltage is equal to IR. So current is equal to voltage divided by resistance. So if we want the current flowing through this first resistor, it's just going to be the voltage divided by this resistance. So it's going to be the 120 divided by the 20, which will give us 6 amps. And if we want the current flowing through the second resistor, it's just going to be the 120 divided by 60 ohms, which is going to be 2 amps. So we have 6 amps and 2 amps. We have more current flowing through the lower resistance loop, which makes sense. Current's going to want to flow through the loop with less resistance. Now, part B, find the total resistance and the total current for the circuit as a whole. So before we calculate it though, what should we get? If we have 6 amps and 2 amps flowing through here, when they add together here, we should get 8 amps. And then we should have had 8 amps here flowing in, breaking off into 6 and 2. So when doing our calculations, we can use it as a check. So the total resistance, again, 1 over RT plus 1, equals 1 over R1 plus 1 over R2. So it's equal to 1 over 20 plus 1 over 60. So 1 over RT is equal to 1 over 20 plus 1 over 60 is 1 over 15. So therefore, the total resistance is equal to 15 ohms. So it's less. Now, that's the total resistance. So if we want the total current as well, the total current is going to be the voltage over the total resistance of the circuit, which is going to be the 120 divided by the 15, which is going to be 8 amps, as expected. So there's 8 amps flowing in, and there's 6 in this branch through this resistor, 2 in that branch through that resistor. So I want you to do some exercises that I've uploaded to Daymap. not these ones. Check the Google Doc for specifications. Cheers.